Welcome to AI Podcast. Today we're digging into a neat AAAI 2025 paper called Knowledge Tagging with Large Language Model-Based Multi-Agent Systems. Short version first, the authors split one hard job into a few small ones, so an AI makes fewer wrong tags on math problems, especially with smaller models. You trade a bit of recall for cleaner, more conservative decisions, and they even ran it in the wild at Squirrel AI with real impact.
I like starting with the punchline, but let's slow down. What exactly is knowledge tagging?
Picture a librarian for math problems. Every problem needs the right shelf label, like reciprocal or two-digit composition. If you tag it wrong, the system gives students the wrong practice. Humans can do this well, but it's slow and expensive at scale.
Right? And the old automation tools?
We've tried dense embeddings, fine-tuned transformers like BERT or T5, and lately a single big model acting like an expert judge. Those help, but they stumble when a concept definition has strict rules or numeric constraints. Think of a rule like both numbers must be tens under 100. A single model might gloss over that detail.
So the twist here is to break the job apart.
Exactly. The system is a multi-agent pipeline. One agent plans the checks, another solves the question if needed, a semantic judger looks at meaning, and a numerical judger actually writes and runs a tiny Python snippet to verify number rules. Then they and all the checks together to decide yes or no.
That's like airport security with multiple gates. Each gate checks one thing, and you pass only if you pass them all.
Perfect analogy. And because the numeric gate executes code, it's less likely to wave through a problem that violates a math constraint.
What did they test this on?
A dataset called MathNoCT. It covers a couple dozen early-grade math concepts. The tricky part is that for every true match, there are several lookalikes that don't match, so the system has to be precise. They compared their multi-agent setup to embedding similarity, fine-tuned models, and a single LLM baseline with a couple of demonstrations.
And results?
The big pattern is higher precision. In plain English, fewer false alarms. For smaller models, accuracy also bumps up noticeably. Think moving from the mid-60s to the mid-70s in accuracy for a representative case. But recall tends to drop because every extra gate is one more way to say no.
So it's stricter by design. Why is that good in education?
If you tag a problem to the wrong concept, a student gets practice that doesn't fit their gap. That's worse than skipping a borderline question. So the authors argue that higher precision is the safer default, especially for recommendations and diagnostics.
Any caveats we should flag?
A key one. No matter which family they tested, Llama, Mixed Trial, GPT, the numeric checker always used a strong model for the code step. That could make the multi-agent setup look especially good against a single model baseline. I'd love to see an ablation where all agents share the same base model.
Got it. And the single model baseline, how competitive was it?
It used random demo retrieval for the examples. That's simple and fair, but stronger retrieval could raise that baseline. So there's room to test a tougher comparison.
How about real-world use? You mentioned deployment.
Yeah, they report deploying the system at Squirrel AI, tagging across a very large set of knowledge points in Chinese and US math programs. The headline is substantial cost savings on labeling, and interestingly, a much faster way to validate AI-generated problems. They say the problem pool essentially tripled after pairing generation with this tagging judge.
That's pretty tangible. Who's behind the work?
Lead author Hang Li, with collaborators including Qingsong. Affiliations include Michigan State University and Squirrel AI Learning.
Nice. Let's unpack the design a little more. How does the planner know what to check?
The planner reads the concept definition like a contract and splits it into small, testable subconstraints. For example, semantic check about what the problem is asking, plus numeric checks like exactly two numbers, both multiples of 10, each less than 100. The semantic judger handles the meaning, and the numeric judger turns those rules into code and runs it on the problem's numbers.
So if the concept is learn to calculate reciprocals, the semantic judge asks, does the problem talk about reciprocals, while the numeric side might check that the operations are the right type and within bounds.
Exactly. And if any gate fails, the final answer is no. That's why recall can dip. One shaky substep can block an otherwise correct match.
Makes sense. What about assumptions in the experiments?
Early grade math only, with English language concept definitions and problem text. Two-shot examples to nudge the agents. An evaluation with accuracy, precision, recall, F1 against expert labels.
Reproducibility check. Any risks?
A few. Using closed models for the numeric agent means replication can hinge on paid APIs. Multi-agent pipelines add latency and cost per decision, and results may not carry over to higher grades, other subjects, or non-English without more testing.
If you were to push this forward, what would you try?
3 things. First, hold the numeric agent constant across conditions, or better, swap it in and out, so we can cleanly measure the benefit of decomposition versus model strength. Second, add a stronger demonstration retriever to the single model baseline. Third, broaden the data set to later grades in different domains, and tune the operating point so teams can pick more precision or more recall depending on the classroom need.
I'd add one more. Publish the prompts and evaluation harness. Even partial release helps other groups stress test the approach.
Totally. And stepping back, there's a bigger idea here. When a task mixes language and rules, don't rely on one monologue from a single model. Break it into a plan, check semantics with language, and check rules with tools.
Right, like a careful teacher. Read the question, check the intent, then roll up your sleeves and do the math on scratch paper.
Exactly. Quick takeaway for listeners. If you're building educational tagging or anything that needs strict compliance with definitions, a small team of specialized agents, including one that can write and run code, can give you cleaner labels, especially when you don't want false positives sneaking in.
And keep an eye on fairness in comparisons and on the precision recall trade-off. Conservative systems are great for safety, but you don't want to hide too many good items either.
Well said. That's it for today's AI podcast. I'm Ben.
I'm Maya. Thanks for listening, and we'll see you next time.